TRAX, Tracking in Complex Sensor Systems.
Hey, my name is Feng. In this presentation, I'm going to talk about proximity report triggering threshold optimization for network-based indoor positioning.
Hey, this is Feng. I'm a postdoc working on the TRAX project at Ericsson, Linköping, Sweden.
So let us start with the motivation of this work. With the rapid development of beaconing techniques, for example, the iBeacon introduced by Apple, we believe that more and more indoor location-based services will be relying on event-triggered proximity report. Here is an illustrative example. When some BLE-enabled mobile device approach to a reference BLE beacon installed at the entrance of a shop, a welcome message will pop up, followed by some advertisement. The idea is essentially similar to cell identification for outdoor positioning. In contrast to the conventional framework, where the received signal strength reports are transmitted periodically, proximity reports are considered to be event-triggered, for instance, when entering or leaving the coverage area of a reference BLE beacon in our framework. Harness of proximity reports in an event-triggered fashion may result in novel positioning system with significantly reduced overall signaling overhead and communication bandwidth, smaller database for storage, as well as cheaper deployment and maintenance cost.
So this is the outline of my presentation. First, I will briefly introduce a conventional way of obtaining a proximity report and further demonstrate the information behind. Then I will give some prerequisites for doing RSS threshold optimization, followed by some experimental results obtained for a live BLE network deployed at LinLab, Ericsson Research, Linköping, Sweden. Finally, I will conclude the talk. A received signal strength measurement is obtained from the power delay profile and represented using 6 to 8 bits in many systems. In the SQL, received signal strength is called RSS for short. RSS measurements are more often used than any other types of position-related measurements, simply because they are easier to obtain. But algorithms using RSS measurements can only provide coarse localization accuracy due to the fast and slow fading error in the RSS measurements. A binary proximity report can be obtained simply by comparing an RSS measurement with a pre-selected threshold, here denoted as P subscript TH. The value of a proximity report indicates whether or not a target is in the coverage area of a reference BLE beacon. For the time being, let's simply assume that the RSS measurements are noise-free and the environment is homogeneous. We can relate an RSS threshold to a coverage radius d as shown in the figure on the left-hand side. Inside the coverage area, the UE will receive a binary bit 1 with probability equal to 1. Otherwise, it will receive a binary bit 0 outside of the coverage area. Moreover, this figure also clearly shows that with only one proximity report, we can only very coarsely relocate the user equipment. In order to mitigate the location ambiguity, we could fuse a multiple of proximity report obtained from different reference nodes. The figure on the right-hand side gives one example where 3 BLE beacons are deployed and 6 smaller regions form as the intersections of the 3 individual coverage areas and the boundaries of the deployment area. In this example, a received vector 010 indicates that the receiver is in the coverage area of the second reference BLE beacon, well beyond the coverage area of the first and the third reference BLE beacons. But fusing a multiple of proximity reports is not always beneficial, unless the coverage radius is carefully chosen. Too big coverage radius, or equivalently speaking, too small RS threshold, and too small coverage radius, or equivalently speaking, too big RSS threshold, does not give sufficiently informative proximity reports. Next, I will show some simple MATLAB animations to motivate the importance of the RSS threshold. In the first example, I set the coverage radius equal to 3 meter. This corresponds to an RSS threshold around -75 dBm. The UE, indicated by a blue circle, moves from the left end of the corridor to the right end. The area filled in a red color indicates the location ambiguity. Clearly, we can see most of the time the location ambiguity is quite huge. In the second example, I set the coverage radius equal to 33 meter. This corresponds to an RS threshold around -95 dBm. Similar to the first example, the location ambiguity is huge. If we can choose the coverage radius more reasonably, for instance, in the third example, where we set it to 10 meters, which corresponds to an RS threshold around -85 dBm, we can see the location ambiguity has been reduced significantly. And then a fundamental question arises as how to choose an optimal threshold so as to optimize our belief in an unknown position. To solve this problem, we propose a statistical framework where the RSS measurements assumed to follow certain distribution rather than noise-free as was assumed in the previous illustrative examples. The proposed framework is very generic and it comprises two key steps. In the first step, some prerequisites need to be fulfilled. These include collection of deployment information, selection of a radio propagation model, and calibration of the model parameters, and the selection of evaluation set of sample positions. In the second step, an RSS threshold is to be selected such that some localization accuracy metric is optimized. I will introduce this in more details in the following slides. The first prerequisite is the deployment information. This includes the building map, floor plan, known positions, and transmit power of all BLE beacons. This figure shows the floor plan where Ericsson Lin Lab locates on. This is also the surface area of our interest. A network of 10 BLE beacons is deployed for indoor positioning. The positions of the BLE beacons are marked by the red stars and indexed in the figure. Next, we need to collect a batch of RSS measurements and fit a radio propagation model to the data. We could choose simple linear models, such as the linear log distance path loss model, piecewise linear model, or choose some advanced nonlinear model, like the most popular Gaussian process regression model. In our work, calibration of the model parameters is done in the offline phase. Here are some more details about the measurement campaign and data fitting. A moderate scale measurement campaign was conducted during normal work hours. Throughout the measurement campaign, the mobile device equipped with BLE chipsets receives data packages from the BLE beacons and measures the RSS. Around 12,000 RSS measurements were collected along 52 predefined tracks. For clarity, we depict the 52 tracks all together in the top figure and use different colors to indicate the quality of the observed RSS. We then feed the data to 3 different RSS models, namely the linear log distance model, piecewise linear log distance model, and the nonlinear Gaussian process regression model. The fitting results are shown for the first two linear models in the figure on the left-hand side, and shown for the nonlinear GPR model in the figure on the right-hand side. The two linear models depend on one-dimensional distance parameter, while the nonlinear model depends on two-dimensional geographical position parameter. Therefore, it is more realistic to use for complex indoor environments. The third prerequisite is an evaluation set of sample positions. Here is an illustrative example where the sample positions in the evaluation set spread uniformly in the surface area, and they are of equal importance. After all the prerequisites have been fulfilled, the optimization procedure becomes then fairly simple. For each threshold candidate, we evaluate some localization accuracy metric, such as localization root mean square error or localization error percentile, for every sample position in the evaluation set. Then we take weighted average of all sample positions to have a localization metric in the mean sense. Finally, we find the desired threshold by solving an optimization problem. In our work, the localization accuracy metric is chosen to be the best achievable root mean square error formulated with the aid of Cramer-Rao bound analysis. This sets a lower bound for unbiased position estimators that are mostly considered in the signal processing society. Alternatively, we could also use other bounds, such as Branking bounds and the Bayesian type bounds. Here, I won't show the math behind this optimization procedure, but this figure shows the best achievable localization root mean square error as a function of the RSS threshold PTH for three different RSS models. It's not surprising to see the convex profile of the RMSE curves in all cases. As was explained before, too high or too low threshold gives very little information about an unknown location. Next, I will conclude this presentation with this signaling chart. In our work, we have assumed that the reference network nodes, namely the BLE beacons, transmit reference signals in the offline phase, and the user equipment collects RSS measurements and further uploads them to a computation entity for central calibration of the RSS model parameters, as well as the threshold optimization. In the operational localization phase, another UE which newly enters the service area will receive the threshold configuration information from the computation entity. This optimal threshold will be used to compare with the instantaneous RSS measurements, and the resulting proximity measurements report will be transmitted to the computation entity for positioning purposes. In a companion presentation, my colleague Yuxin will introduce a proximity reports-based particle filtering algorithm. Thank you for your attention.
For more information about TRAX, please visit our site at trax.u20.nl.